Hello again. I'm back with another video related to using integration method to find deflection of beams. And this would be our last example for this particular section, using integration to find deflections. And the intention of this problem is to show you that actually if you have to cut more than one section to find the internal moment, which is the case here, as you could see, we have a cantilever beam with one load right in the middle, right here, and then one load at the far end. And you see the moment in section AB is going to be different than the moment in section BC. And first of all, how would this guy deflect? So it would deflect like this. And the maximum deflection would be right here. And that's the intention. We want to find the maximum deflection, which would be deflection at point C. Okay, so as I said, the intention is, or the objective is to show you that it's a tedious task, even for even a simple problem like this one, which we only have to cut two sections. Now imagine if you have to cut more than two sections and, get the moment equation in each section. It's going to be really time consuming. So anyways, what I did here first, I found the reactions at point A. So 2p would be the force reaction, and the moment of these forces about A. When you add them up, you get 3pl over 2. And then cut the beam somewhere between A and B, right? And get the equation of moment. Notice now this would be the moment in section AB. Now I've taken x to be taken from A. So x would be from right here. And I'm going to use the same x over here for section BC. Anyways, we get the equation of the moment to be 2px minus 3pl over 2. But remember, this equation is only valid from A to B, which means from 0 to L over 2. Okay, we'll do the same thing over here. Remember, we haven't changed the reference. Even though we could do this problem actually for section BC, we could use x from this side if you want, but I'm not going to do that. I don't want to, create problem and confusion. So let me actually remove this guy here. Put the load back. Okay, so we are using the same reference, which is point A. X starts right there. Okay, cut the beam somewhere between B and C. Find the internal moment. I'm going to call it M sub BC, right? Because that's a moment between B and C. Notice that here the moment of this P here would be P times X minus L over 2. That would be this distance. Remember, this is X minus L over 2, right? Anyways, you get the equation for the moment. And remember now, this equation is only valid between point B and C, L over 2 to L. Now I start the integration process. So we'll start with the section AB. We set EIY double prime equal to the moment. Integrate, you get a constant of integration C1. Notice that C1 we can easily find because we know exactly what the boundary condition is at point A. At x equals 0, y prime is 0, therefore C1 becomes 0. Now, we integrate one more time and we get the equation of the elastic curve right here, the deflection curve between A and B. And then we get another constant of integration, C2. Again, we have a boundary condition. Obvious boundary condition is that x equals 0, deflection is 0, so C2 becomes 0. So I have both equation of slope and equation of moment. But what good is that? Right now, it's not good for me because I want actually the equation of the elastic curve between B and C. I want the equation of this curve in order to find the deflection. But you see how we're going to approach that in a minute. So let's go ahead and integrate here. We integrate once, we get a constant C3, but there's no boundary condition. What do I know about that section? Nothing. So I continue integrating to get the equation of the elastic curve. So I have so C3 is not determined, so I have the integral of that becomes C3x plus a new constant C4. So how do we find C3 and C4? See, the objective is to find the equation here. If you have that equation, then you're done. just set x equal L, and that would be your maximum deflection. But how do you find C3 and C4? That's where we use what we call matching condition. So far we have used boundary condition, now we use matching condition. So let's go, a matching condition, let me actually, before we move to the next page, tell you what matching condition is. Right at this point, where these two elastic curves are, they come together, at this point, the slope has to match and the deflection has to match. So the slope and the deflection, in other words, this equation, this should match what? This guy at x equal L over 2 at point B. And same thing here. This equation, deflection should match this equation right here at x equal L over 2. And that will give us two equations. We have two unknowns. We should be able to find C3 and C4. Okay, matching condition. As I said, at x equal L over 2 point B, we match the slopes and we match deflection. So go ahead and set them equal to one another. I suggest, guys, you put a piece of paper in front of you and go over this on your own. So that way you see what you're doing. So what I did here, I set the slopes equal to one another. I solved for C3. Now, I didn't even plug in x equal L over 2 till the end. When you plug in x equal L over 2, this is going to be your C3. All right. Also, I matched the deflection between the two elastic curves. Again, I cleaned it up. I found C4. I didn't even put x equal L over 2 till the end, and I got C4. Now remember, I go back to this equation right here, right? This one. I plug in C3 and C4, which they are right here, C3 and C4, right? Put them in here. Now you're all set. This is the equation you wanted. This is the equation you wanted. And now, where is the maximum deflection? Maximum deflection is right here when x equal L. So put x equal L, and if you just work this out, do the algebra, and you get minus 7 over 16 PL cube over EI. Negative just means downward. Now, the good news is this, that for beams with many load changes, and which means you have to get different internal moment equations and then integrate so many times and so many boundary conditions, so many matching conditions. The good news is that there is a method called superposition, which I'm going to actually have a PowerPoint, hopefully narrated for you. And I'll come back and I'll do this problem. And you'll see actually this problem that it took us maybe, if I was going to write everything down, it would have taken us probably 15, 20 minutes. I'm trying to cut it down under 10 minutes of talking. And I'm really talking fast here, as you could see. Anyways, the same problem, I'll do it for you in about 2 minutes or less. And that is using what we call superposition, which is basically using the charts and tables. Okay, so stay tuned for that problem. Shortly, it's almost 10 o'clock Sunday night that I'm doing this video for you. I'll come back soon and hopefully tomorrow and show you how you can do this problem much faster and easier. As always, thanks for watching and listening.